Okay, third page here, power. So the rate at which work is done, it's basically work divided by time. Okay, this is the average, so average power is work divided by time. It's measured in watts. A watt is a joule per second, and so this is normally how you'll see them written. So let's see, average power, we have work divided by time. Work is force times distance. Distance per time is velocity. Cool. So force times velocity will give us power. And then taking into account the fact that the force will not necessarily be in the direction of motion, but will have some component in the direction of motion, we throw the cosine theta in there. So if the two are in the same direction, so if it's going this way, let's say we have a block here, and the force being applied is in the same direction, the angle between them would be 0, and the cosine of 0, you know, is 1. So this formula just becomes this formula when the force is in the same direction as the direction of motion or velocity. And just a little side note, 1 horsepower is 746 watts. I know elite cyclists can produce something like 500 watts for extended periods of time. We did an experiment in physics class where we measured our power output, and you know, it was like 1 or 200 watts, and that was just for a couple minutes. So yeah. Momentum and impulse. Alright, so this was touched on briefly in part 1, I think, but let's see. Using F equals ma, and acceleration is change in velocity per time, and momentum is mass times velocity, remember P for momentum, we can say F equals ma, which is m delta v delta t, which is delta, so this would be delta p, or change in momentum, and that's how we get this formula that I showed you. So this is more specifically impulse of force, change in momentum, and change in time interval. So let's see, impulse is defined as the change in momentum, where we can, this sort of more interestingly, or perhaps more usefully, we actually calculate the force involved in an object changing its momentum over some time interval. I have a great video that I need to show you, and I wonder where that is. I know where it is. I wonder if we can do this. Actually, let me finish this page, and then we'll switch over. So, conservation momentum. Alright. So, a couple definitions. A closed system is a system where no mass enters or leaves the system. So, if it's like, you know, pool table, 8-ball, corner pocket, whatever. So these are going to collide, right? And you're using conservation momentum to find the velocity of one of the balls afterwards. We would say that these two pool table balls are the system that we're talking about, and we would forget about the earth and the pool table and all that stuff. An isolated system is a system where there's no net external force acting on the system. So when these two things collide, the forces involved are simply between the objects. If we were to do something like put the table at a slant, can I rotate this? No. If we were to do something like put the pool table at a slant and talk about a collision, all of a sudden there would be some net force acting on the system, and that would be gravity, and we would say that that system is no longer isolated. Okay, within here there's no net external force. Sure, there's forces happening between the objects, but there's nothing from the outside actually pushing the entire system in a certain direction. That is, of course, neglecting friction, which we do frequently. And then, for collisions, we have elastic and inelastic. So just sort of memorize this basically. Elastic, I think bounce. This is where both kinetic and momentum would be conserved. Whereas in an inelastic collision, this is where, you know, it's a car crash or the objects stick together. The baseball player catches the baseball. Okay, it doesn't bounce off his or her head. It can also be a partial bounce. So for example, this will be cool. Boing, 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 boing. Okay, so that bouncy ball was bouncing, but it didn't go boing, boing, boing up to the same height. Okay, notice that it was only a partial bounce. So that's an inelastic collision happening there, where down here some of the energy is lost in the form of heat, or maybe you actually hear, you know, with my voice, you hear the boing, 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 so some energy is lost due to sound. It produces sound. So in collisions, we say that the momentum before is equal to the momentum after. So the total momentum of the system before is equal to the total momentum of the system after. And this is what you're probably familiar with. mv plus mv equals mv plus mv, where it would be the momentum of one of the objects plus the momentum of the other object before the collision equals the sum of the momentums after. Now in 2 dimensions, so we will do some crazy questions where it's like there's an object like this and then an object like this. See how it's offset and it comes in, and then afterwards they like one flies off in this direction and the other flies off in this direction. Oh yeah, that's going to be pretty cool. So how we solve that is basically we consider the horizontal momentum and the vertical momentum separately, where, and I know you're shaking your head saying, oh my gosh, this is going to be so fun, where for the final momentum here, you know, we're using SOHCAHTOA and we have some vertical momentum, and for this object we have some vertical momentum as well. So we would have something like this vertical component of momentum is going to cancel this vertical component of momentum, because if this was at rest and this moved in horizontally, there was no vertical momentum to begin with. And the horizontal momentum of this object, again if this were at rest, would be equal to the sum of this horizontal component of momentum and this horizontal component of momentum. Okay, so we will see that shortly. And here, here's the video that I want to show you. This is totally related to impulse, so take a look. So that's a golf ball, right? It was obviously going very fast, and it's bouncing off of a hard surface, a wall, and it's doing so in a really, really short period of time. Okay, so it looks like, all right, 70,000 frames per second. Okay, so and 150 miles an hour. Whoops. Oh, maybe that was it. But the idea is that the golf ball has some momentum in this direction, and then almost instantaneously it has some momentum in this direction. So when we talk about change in momentum, it had some change in momentum, and it happened over such a small period of time where, like, let's just pick a number, 5. If you divide that by 0.00000, let's see, 1, okay, and you divide, that's actually 5 million, all right? So 5 divided by 1/1,000,000th is 5 million, and I'm just making those numbers up, but to illustrate a point that when this number is real small, the force involved is very large. So let's watch the force involved in changing the momentum of the baseball and be amazed at how, why is this not working? And be amazed at how, oh, maybe I'm done being able to play that. Oh well. But, well, you saw it once, and it was amazing. The golf ball was severely deformed because the force was so great.